So to think about numerical integration, it helps to often consider the integral as the area under a curve. So let's say you have a set of axes, x on the horizontal axis, and on the vertical axis you have f of x. And let's say your f of x is some sort of curve, and you want to find the integral of f of x between points A and B in x. And of course that means that graphically we represent this integral as the area under the curve, between the curve and the x-axis, from points A to B. Right? So this area, A, is equal to the integral from A to B of f of x dx. Now this graphical or area or geometric representation of the integral makes it really easy to understand how you can use the rectangle type rules to approximate the integral. So for example, take this particular illustration of an f of x. It is x squared plus 1. F of x equals x squared plus 1. And as an example, we want to integrate this function between x equals 1 and 3. So this integral from 1 to 3 of f of x dx is approximately equal to, now what we're going to do is we're going to break up this integral into multiple areas under the curve. So one thing that we can do is we can say, all right, well, here's a rectangle. And this is one area under the curve. Here's another rectangle. And here's another area under the curve. And we're just going to add those two together. So we have our integral is approximately equal to the first area plus the second area. Or in this particular case, f of x0 times x1 minus x0 plus f of x1 times x2 minus x1. Right? So in this particular case, x0 is equal to 1, x1 is equal to 2, and x2 is equal to 3. This is what's known as the left-hand approximation, or LHA. And you can see that this formula is exactly what I have drawn here, because you have f of x0 is the height of the first rectangle times the distance between the two x's, x1 minus x0. So height times width of the rectangle gives you the area. And the second one, of course, you have the height, f of x1, times the width is the second area, which is corresponding to the second term in our approximation. This is called the left-hand approximation because we're evaluating the function at the left-hand side of the interval of x, in this case like x1 minus x naught. We're evaluating the function at the left-hand side of that interval in both cases. So this is the left-hand approximation. Another thing that we can do is we can do what's known as the right-hand approximation, in which case we would, the first area would be the one that I'd already drawn, and stacked on top of that, the one on top that's hatched in the opposite direction here. And the second area, of course, being much taller as well, being the sum of these two rectangles from 2 to 3. And that would be known as the right-hand approximation. Right? And so in that case, our approximate area, or our integral, is area 1 plus area 2, is equal to, instead of f of x0, you have f of x1 times x1 minus x naught. Plus, instead of f of x1, now we have f of x2 times x2 minus x1. And this again is the right-hand approximation, or RHA. And of course, what would be really nice is if we could have a more sort of average approximation. As you can see, the left-hand approximation, if you have an increasing function, in this case we do, then it underestimates the integral. The right-hand approximation overestimates the integral. So it would be nice if we had some sort of average between the two. And what we could do is we could say, well, there's also another x in here, x equals 1.5, and if I evaluate the function at x equals 1.5 and make that my area, 1, and also evaluate the function at x equals 2.5 and make so my area, then I will have something that's a little bit more accurate. So in that particular case, this would be a midpoint approximation. Then our area 1 plus area 2 is equal to f evaluated at this fictional point, x, where I is equal to a half, times x1 minus x0, plus f evaluated at this other fictional point, x 1.5, times x2 minus x1. And that's cool. Now notice in each one of these I should say this is called the midpoint approximation. And one thing that I should say is notice that in each one of these approximations, our interval, x1 minus x0, is the same every time, or x2 minus x1 for the second term, is the same every time. What's changing is what point we're evaluating our function at for each one of these terms. So for the left-hand approximation, it's the left-hand side of the interval. For the right-hand approximation, it's the right-hand side of the interval. And the midpoint approximation, it's the midpoint of the interval. Now, I didn't define for you what this x half is, this fictional point, and x a half is just the midpoint between x1 and x0, so that would be the average between those 2 points. And x 1.5 is the average between x1 and x2. Now, I say they're fictional points, and I put them in quotes, but if you have this function, as we do in this particular case, if we scroll back up, we notice that the function is f of x equals x squared plus 1. So we have the function, but because of that, these points are not fictional. We can just evaluate the function at the midpoint, and that's fine. But what happens when we don't actually have points? The function that we can write down and evaluate wherever we want. In other words, the question is, what's wrong with a midpoint rule? And that is, it assumes we can evaluate f wherever we want. That's not how you spell wherever. Wherever we want. In other words, not just at x0, x1, x2. But that's not always the case. Again, what if you have experimental data points, or if it's really, really expensive to evaluate f at multiple points, and it takes a lot of computation to do so, so you want to avoid that as much as possible, and you already have a certain number of points that you've been given, or that you had to calculate for other reasons. So we want to avoid evaluating the function at other points. So if you did want to do the midpoint approximation, so let's say we want to do the midpoint approximation, definitely if we can, but we can't evaluate or don't want to evaluate f at points other than some discrete set of points that have already been given to us, how would we do it? And we'll get to this later in a few minutes. In a few. Okay, so in general, what we can do is we can make a general formula for these approximations for n plus 1 points instead of just 3 points that I showed you before. The integral, or the area, is approximately equal to, for the left-hand approximation, it's the sum I equals 1 to n of f of x I minus 1 times xi, the interval xi minus 1. That is the left-hand approximation. And note that this delta x here, or this difference between the two x's, is just some delta x, which in some cases it may be constant, right? So you might have your discrete points at equally spaced intervals, in which case you can just substitute delta x in there for the formula. So that's your left-hand approximation. Your right-hand approximation is the sum I equals 1 to n of, now it's f of xi instead of f of xi minus 1. Notice the difference between the two. Times your delta x. I guess I should write it all out. So xi minus 1, right? So this is also delta x. This is your right-hand approximation. And finally, the third one that I showed you, if you can do it, you have the sum of I equals 1 to n of f evaluated at 1/2 xi minus 1 plus xi, so that's the midpoint of the interval, times the interval again, xi minus xi minus 1. And that again is the midpoint approximation. And so these are the three rectangle rules that you could do. The first two, the left and the right-hand approximations, are ones that you should be able to do because you probably will have discrete points. This midpoint approximation depends on whether you can evaluate f at whatever point you want. Maybe you can't, in which case maybe the midpoint approximation is off the table for you. But unfortunately, the midpoint approximation is superior in terms of its accuracy. So the question is, what would you want to do to improve your accuracy, but if you can't, in the case where you can't do actually the midpoint approximation?